So let us look at example 8, where you are asked to calculate the ratio of two functions. Right? So you have a function for x tends towards here is positive infinity. For a polynomial which is of order 2, I call this P2. And then we have a polynomial of also order 2, I call this Q2. Okay, so like P2 and Q2 are two different polynomials of this form. So in order to calculate the limit of a rational function, we have to try to cast the rational function into the form that is expressed in terms of 1 over x. Okay, so we have to somehow translate this rational function into the form that has only expression of 1 over x. If you are able to express p over q into a function that involves only 1 over x, then you'll be able to make use of the previously known results that the limit of 1 over x tends towards 0 when x tends towards infinity. Okay, so the first step of calculating the limit of this rational function is to try to express all the functions, including the denominator function and numerator function, into the form that involve only that expressed in terms of 1 over x. So what you do here is this. So here, let us copy down the function of 5x. So the p upstairs is 5x squared plus 8x minus 3. And downstairs is a function of 3x squared plus 2. Okay, so what I'm going to do is that I'm going to try to convert this expression into the form that involves only 1 over x. So what I'm going to do is this. You pick the highest order of the x term, both in the numerator and in the denominator. So the highest order of x is x squared. So you pull out the x squared term, and you pull out the x squared term in both the upstairs and downstairs. So you pull out the x squared, then you express this as the product of x squared times the other thing. So this other thing is easily written down as 5. So 5 times x squared gives you this term. And if you pull out a factor of x squared term, then what you are left is a factor of 8 divided by x. Then for this term, we pull out an x squared from this. So what you left is a factor of 3 divided by x squared. So now you have successfully re-expressed this in terms of the product of x squared and the other expression in terms of 1 over x. So if you pull out a factor of 2 upstairs, you also pull out the factor of x squared downstairs, so that the x squared term that you pull out from the numerator and denominator could be cancelled off later. Okay, so you pull out the same factor of x squared, then you're left with 3 plus 2 over x squared. And then x could get cancelled off. Then you're left with this expression. So now it is then quite straightforward to calculate the limit of the function. So the limit of this function when x tends toward positive infinity is the same as the limit of this expression when x tends towards positive infinity. So here I have a limit of x tends towards infinity for the case of 5, and I have a limit of 1 over x when x tends towards infinity with a constant 8 pull out minus 3 times the limit with x goes to infinity for the function of 1 over x squared. So this is the expression for the denominator functions. Okay, this is the expressions for the limit that involve the numerator function. So the same thing also goes to the denominator function, which is the limit of 3 when x goes to infinity. This is a factor of 3, then plus 2 times the limit of x goes to infinity for 1 over x squared. So the limit of 1 over x squared when x tends towards infinity has been discussed earlier on. I think has been discussed earlier on when we was discussing example 7b, right? So limit of 1 over x squared is just a product of the two limits of 1 over x when x tends to positive infinity. So anyway, 1 over x squared is 0. So here I am quite comfortably write down the results of the next line. So here the limit of 5 remains 5, and this limit is shown to be 0. So 8 times 0 is 0, plus 8 times 0 minus the 3 times the limit of 1 over x squared when x goes to infinity, and this is a result of 0 that has been shown in the previous example. So divide by a constant of 3 plus 2 times 0. So what is left is just a number, which is 5 over 3. So this is the result of the limit for this example. When x tends to approaching infinity, you end up with a constant. So what this means, if you translate this example into the form of a graph, is as follows. So you have a functions which is made up of some ratio of two polynomials. Three x squared plus 2 x tends toward plus infinity is a value of 5 over 3. So these statements can be translated into this form, right? So you plot a function of x and y, and when x tends towards infinity, you are looking at the region which is far away from 0, right? So in the limit where x is very large, the functions will tend towards a constant. So if you were to look at this, you draw a line of the constant 5 over 3. These statements of limit of this rational function when x tends towards infinity is 5 over 3 means the function will finally tend toward a constant like this. When x is getting very large to infinity, the functions would then behave as like it is getting very close to a constant, but never touch the constants of 5 over 3. When you plot the graph of the function in example 8, you get this, and you can see that the line of y equals to 5 or 3 is the so-called horizontal asymptote, and the function would tend towards the asymptote when x tends to very large. The same argument could also be applied to the limit if the x is tending in the opposite directions to minus infinity. In this case, you will find that the functions will tend towards the asymptote of y equals to y over 3 as x is tending towards minus infinity. So we are going to talk about example 9 again, which is a functions of the ratio of two polynomial. The important thing to note here is that the rational function is made up of a function upstairs, I call it P1, and function of P3, where P1 is a function of order 1, P3 is a function of order 3. This is in contrast to example 8, where the rational function is a function of P2 versus P2, Q2, where both P2 and Q2 are polynomial of the same order. Here we are talking about a rational function where the order in the polynomial upstairs is less than the polynomial in the downstairs. So before you can actually work out what is the limit without using any theorems, you could actually guess what is the behaviors of the function as x tends to very, very large. So here you are comparing two functions, x11x plus 2, and compare it with 2x cubed minus 1. So as x grows larger, do you think which one would get closer to infinity faster? Is this function going to become larger faster than the function downstairs? When I say larger, okay, imagine you have a function of, say, p1, right? So p1 is proportional to x. So obviously when x goes to very large, you expect p1 to go to infinity. But how about the function of p3? p3 is also going to be infinity when x grows, right? So since the polynomial downstairs p3 has an order higher than the polynomial of p1, you would expect the functions of p3 would goes at a rate which is faster to infinity than the p3. So you are talking about the behaviors of the functions between p1 and p3. Here, what we are comparing is the functions of p1 and p3 that both goes to infinity. So we expect that as the functions of x, well, the values of x, if it grows to larger, then p1 would go less fast than p3. Okay, this is p3, this is p1. So here is just a very simple representation of the fact that the rate of p3 grows larger is faster than the rate of p3 growing. So you expect that when x become very, very large, if you take the ratio of p1 over p3, so this grows large, but this grows much larger at a faster pace than the function which has a lower order. So you would expect when x to become very large, then finally p3 will win up as compared to p1. So that means p3 will grow much faster than the values of p1, and finally the behaviors will be sort of like taken over and dominated by p3. So p3 will become much larger than p1, and finally it will go in such a manner that it will become like 1 over infinity. Okay, so that is the kind of intuitive expectation you would expect of the ratio of these two polynomials. So indeed, you would actually show that the limit of this function is going to be 0 without using, well, by using the limit theorem. So let's just write down formally the behaviors of 11a plus 2 over p3 2x cubed minus 1, and this is to be evaluated when x to become positive infinity. So let us try to formally evaluate the limit of this rational function. The previous argument I was talking about when I refer to this behavior is an intuitive expectation based on the expressions of p1 and p3. So this is not considered as a formal calculations, but you could still able to sort of like project what will happen when x goes to very, very large. You expect that the ratio of the two functions will go to 0 based on just by looking at the rate of growth that depends on the highest power in the rational function. But here we are going to prove the limit by using a more appropriate formal procedure. That is, we will try to pull out the highest factor from the rational function. So let us look at this one. What is the higher power? The highest power is the x raised to the power of 1. So we would pull out the x from the denominator function. When you pull out a factor of x, then what is left is 11 plus 2 over x. And downstairs, you pull out the highest factor, right? The highest factor is x power 3. So you have x power 3, then you have factor of 2 minus 1 over x power 3. Right, so that is what we have. So here you can continue to write down. So here x going to be infinity. So you would write down the next line of equation by using the theorem that we have just discussed in the theorem number 8. Right, so we are going to use first the quotient rule. So the quotient rule would say that this is equals to the ratio of the limit x goes to infinity in the upstairs divided by the limit of x goes to infinity for the function downstairs. So upstairs and downstairs. So here x is a number that could be cancelled off, and when cancel off you have a factor of 2. Okay, so the upstairs functions or the numerator function will just left with 11 plus 2 over x, whereas the denominator function will be left as x squared and 2 minus 1 over x cubed. Okay, so this is the first thing you can do, but by looking at this, then you can actually also see quite clearly what will happen. So here the limit upstairs is easily expressed and calculated. It will be just equals to 11 plus 2 times the limit x goes to infinity of 2 over x divided by the limit of x squared 2 minus 1 over x cubed. Okay, so I think that would be slightly complicated. Maybe I should not use these theorems at this stage, because here the x squared is going to be infinity when I pull this out to infinity, right? So but this term is going to be finite, but this term is going to give me some kind of trouble. Therefore, I reckon that it is not quite appropriate to use this methodology of extracting only extracting the x from the numerator, but extract x cubed from the denominator. I should have actually done do these questions in a different way. So I'm going to try to do this again. Instead of pulling out factor of x from numerator and x cubed from the denominator, I'm going to do the other way. That is, I'm going to pull out the factor of x cubed from both upstairs and downstairs, instead of pulling different factors from the downstairs and upstairs. So let me try to write this factor again. So the function is 11a plus 2. So here I have 11. I'm going to write this over again. X goes to infinity. Okay, so let me see what I should do. So I'm going to write this as the limit of x going to infinity. So that upstairs, I'm going to pull out a factor of x cubed instead of pulling out factor of x on it. So I'm going to pull out x cubed, 11 over x squared. I think that is a more appropriate way. Then I have 2 over x cubed. Downstairs, I will pull out factor of x cubed, and I have 2 minus 1 over x cubed. I think that is a more appropriate way of treating these limits in a more transparent manner. So here I'm going to cancel off x cubed and x cubed upstairs and downstairs. So here I'm left with the limit of x going to infinity for 11 over x squared plus the limit of 2 over x cubed, x going to infinity. So this is what is meant for the numerator functions. And then downstairs I have limit of x goes to infinity for a factor of 2 minus limit of x going to infinity of 1 over x cubed. So now this looks very easy to solve. Okay, so here this is a constant and this is 1 over x squared. So the function of 1 over x squared will give you 0. So this has a limit of 0. So is the limit of this is going to be 0. This is x cubed, right? So if 1 over x squared goes to 0, then 1 over x cubed would go to 0 even faster. So this is 0, this is 0. So when I said limit of 1 over x cubed goes to 0, what I actually mean is that I would take 1 over x cubed as the product of 1 over x squared times the limit of 1 over x. Both goes to infinity. So previously we have discussed this. We have also proven these statements of 1 over x will go to 0. Therefore, 1 over x cubed is 0 times 0, where this 0 is the result of 1 over x squared and this is the result of 1 over x. So either way, both would go to 0. Both will go to 0. Then here, the limit of 2 is just 2. So the numerator upstairs is just 0 plus 0 over 2 minus the limit of 1 over x cubed, which is also 0. So it turned out to be just 0. So that proves the limit of the example 9 as 0. Okay, so if you represent this into the graph of the rational function, so this is the limit, right? So you can see that for the limit to occur at infinity, the limit is actually tending to 0. Okay, so when x is very large, the values of y will just gets closer and closer to 0. If you were to look at the calculation I showed you again, the calculation that is mentioned here should also apply even if x is going to negative infinity. Okay, so it can be also trivially proven that x going to infinity, the rational function is also going to 0. And this fact is represented by this part of the line where when x tends towards minus infinity, that is when x is becoming larger and larger towards the negative directions, the values of the function will just tend towards 0. That's why it tends towards 0 as well. So whenever x is in positive infinity or negative infinity, both the function will tend towards the values of 0. Okay, so this limit of the functions is what we call the horizontal asymptote. Okay, so for example, 1 over x, when x tends to be infinity, y will tend to 0. When x tends to negative infinity, the function of 1 over x is also tending to 0. Therefore, y equals to 0 is what we call the horizontal asymptote for the function 1 over x. In the case of the rational function, y equals to 0, this line is also the horizontal asymptote for this function. Whereas for the case of example 8, for these rational functions, you can see that y equals to 5 over 3 is the horizontal asymptote for this function. It is a constant that the function tends towards 2 when x is approaching plus or minus infinity. Okay, so this is the definition of an asymptote. So here, a horizontal asymptote that has this behavior is so defined. Okay, so in this particular example, the horizontal asymptote is the same. Okay, whether x goes to positive infinity or negative infinity, if they tend to a constant, then you have an horizontal asymptote. Okay, but you have to be a little bit careful. Sometimes the horizontal asymptote for x tends towards negative infinity and x tends towards positive infinity may be different. Okay, so in the example we have just shown, the horizontal asymptote for x tends towards plus or minus infinity are the same. So is in the case of this function, the horizontal asymptote is the same, where where irrespective of whether x is going to negative or positive. So in this case, the x, whether is going to positive or negative, the constants is still the same, the horizontal is the same. But in general, this may not be the situation, may not be, okay? It doesn't mean that it's always like that, but it just may not be. That is, it is possible that when x tends towards some positive number, the horizontal asymptote may be different than the horizontal asymptote that happens when x tends to negative infinity. In general, this is possible, but we are not going to show any example of this sort.